topic for this lecture is Mutable References. So we'd like to extend this simply typed lambda calculus with something called Mutable References. So mutable references are called sometimes just references. And mutable references are like pointers. So if you have a pointer, it is pointing to a memory cell, and you can update the contents of this memory cell with this pointer. And references are something like pointers. So if you have reference, it is pointing to a memory cell, like a heap cell, and then you can store a value in this heap cell. And later you can dereference this reference. Basically, you can dereference this memory cell and retrieve the value v. Or you can even update the contents of this memory cell with a new value, for example, v prime. Such is almost like manipulating pointers in imperative languages. But these mutable references come with types, and they also guarantee type safety. So let's start with the language construct for mutable references and see how these new constructs work informally. So we'd like to introduce three new constructs. Reference E. Ref E, this is the keyword. And we'd like to introduce this bang E for dereferencing. And we'd like to introduce new construct, this update or assignment. E colon equal E prime. So this construct is used to create a new memory cell, new reference. So suppose that expression E eventually produces value v, then later you'd have ref v. And now we allocate the new memory cell and initialize it with this value v. And this memory cell is going to have a reference or location. Let's just say location L is pointing to this new memory cell. This is called the location. So locations are basically another name for references or mutable references. And we return this new location L as the result of evaluating this reference V. So in summary, this construct, reference E, is used to create a new memory cell, and it is going to return a fresh location. So what about this dereference expression? So suppose that expression E eventually produces a reference. So this expression E is supposed to evaluate to a reference, not an integer or Boolean value. So if this is well typed, then probably we will have something like a bang L. Now suppose that at this point, location L is pointing to a memory cell with the value V. And now we are going to dereference this memory cell. We are going to dereference this location. So this produces value V. So this is basically dereferencing a location, just like dereferencing a pointer in the C programming language. And what about this expression? This is the assignment, assign, or update expression. So if this is well typed, probably the first expression E will produce a location. And the second expression, this one, will produce some new value V. Now, what happens is, suppose that at this point, location L is pointing to a memory cell with value V0. Now, we are going to override, we are going to update this memory cell by erasing this one and write a new value v. So the content of this memory cell has been updated with this new value v. And so it has this side effect of updating this memory cell, but this expression itself has no interesting computational value, so we are going to return unit. So again, this reference expression, the reference E, is going to create a new memory cell, and it returns the location for this new memory cell, or this heap cell. And this bang E, this dereference expression, is going to literally dereference this location L. So it is returning the value, whatever value is stored in this memory cell associated with this location L. And this assign expression is going to update the contents of the current contents of this location L. So if L is pointing to this heap cell or this memory cell, and if we don't need this value anymore because we are going to update it. So if this is v0, then it's going to be erased, and we are going to write a new value v. So we are going to introduce three new kinds of expressions to support the mutable references. So before we develop the abstract syntax and operation semantics, and finally the type system for mutable references, let's see an example. So we'd like to exploit this reference expression and bang E for dereferencing, and this assign expression to simulate, to implement integer array. Because we don't have actually array, we don't have array in this language. So we have to simulate this integer array using references and integers. We assume that base type integer is already given, and we'd like to exploit this integer base type and the type for this reference, which is written ref a, to simulate this integer array. So this reference A is the type for location that is pointing to value of type A. So what that means is that suppose that location L is currently pointing to a memory cell that contains value V of type A. So literally this location L is pointing to a value of type A. Then later we will see that this location L is going to have type ref A. So that's the type for ref. So notice that we use the same keyword ref in different contexts. So here is ref is a part of expression, and here the same keyword ref is a part of type. So the goal now is we'd like to simulate this integer array type. And the idea is we simulated this integer array with reference of type integer arrow integer, where the first integer is an index into the array, and the second integer is the content of the array. So this integer array is simulated as reference into arrow int. So therefore, this is going to point to a memory cell, and this memory cell contains this function lambda abstraction, which takes integer and returns an integer. And this input integer is the index into the array, and this return integer is the value that is stored in the array at the given index. So that's the idea. So unlike the conventional arrays whose index starts at 0, we simulated this integer array with the function. So there are, of course, several limitations. For instance, the first is there is no restriction on the range of index because it is just an integer, and it doesn't specify the range of integers that can be used as the indices. And we also have to say something about the initial value. And for simplicity, let's just say this integer array is initialized with 0 in all its elements. So the index can be any integer. So for instance, you can even have negative indexes into this array, and the elements are all initialized as 0. So now let's simulate this integer array using these references. So we are going to implement the 3 constructs. First, the new, and this construct is going to create a new array. So it has a type unit arrow integer array. So for instance, if you apply this new to this unit value, and this one eventually creates an integer array. This is integer array. And the second is access. We should have some way of accessing the element of this integer array. So the type is give me an integer array and give me an integer, the index. This is the index into the array. And then I'm going to return the content of the element, the array, the element of the array at this index. So this is the value. The element of the integer array. So we also need this access construct. And finally, just like ordinary arrays, we should have some way of updating the content of this integer array. So we introduce this update. This update says, give me an integer array and give me an index, which is the type int. So this is going to be index, and give me the new value at this index. So this is integer, but this is a new value. Then I'm going to update this integer array at this index with this new value. And after that, I'm going to return unit. So simulating this integer array boils down to implementing this 3 construct: new, access, and update. So let's first try this new. So how can we implement this new? So remember that, so always remember integer array is simulated as reference integer arrow integer, where the first integer is index and the second the return integer is the element. So actually it's pretty easy to define this new. New is give me some unit, but the name of the argument doesn't matter. So let's use this wildcard pattern. So unit, and now I'm supposed to return an integer array, but integer array is reference integer arrow integer. So you are going to create a new reference. So you should have reference here, and inside you have to return this function of type int arrow int. So it's basically mapping from index integer to element integer. So let's create so here Here, let's create a value of type int arrow int. So it says, give me the index. So this is the index I. Then I will return the value at the index I. But we assumed that this integer array is initialized as zeros. So every element in this integer array is going to be 0. That's the way that we initialize this integer array. So you just return 0 here, assuming that integer is one of the base types. So this is how we implement a new. Now let's implement access. Access type this one. So give me an integer array. Let's say this I a. Okay, so this is integer array, and give me this one, an index I. Now we are supposed to return the element of this array at the index I. So it's time to dereference this reference. So A has a type integer array, so it is reference integer arrow integer. So first you have to dereference this variable A. So you dereference with this bang A. And what's the type of this bang A? It is integer arrow integer. So now it's a matter of applying this function to this index I. So this is quite confusing. So this bang A has a type integer arrow integer. So by applying this function to an integer, and this is the index where the value that you want is found. So just apply this one to index I, and you will return the integer, the element at the given index. So this is how you implement access. Finally, let's implement update. Update construct for updating the contents of the given array at the given index. So let me first give the correct answer and then a wrong answer. And actually for this particular problem, the wrong answer is more interesting and more instructive. And actually, so let's first see the correct answer. So this update function takes an integer array. So let's say it's lambda a integer array. So now you have access to this integer array, and then we need an index. So let's index I, and then we need a new value. So this is, let's say, value v, integer. Let's say this is n. So the goal is we'd like to update this integer array A by assigning new value n at index I. So in the syntax of C programming language, A of I now will be n. So basically we want to execute some command like this. The index I of integer array A is now updated with the new value n. So to simplify the notation, let's introduce let construct. So let x e in e prime is basically lambda x for some type A e prime applied to e. And the meaning of this let construct should be familiar from the functional programming like OCaml. So let's just assume that there is a language construct, syntactic sugar is let construct. So let me show you the correct answer first. The correct answer is currently A is pointing to a function because the integer array is simulated as reference of integer arrow integer. All right. So A is currently pointing to a function of type integer arrow integer. So let's make a copy of this one, or let's keep so let's dereference. So let's dereference A with the bang A. So let's create a copy of the current array. So let's say this is old. So let's say now we have access to the current integer array before the update. So after this update, this will not be the value of this bang A, but at this moment you dereference this integer array, and now you have this old. So now this is basically old. Now you have this old array. And then we have to update this array because we are updating one of its elements. So what we do is we update this A with new array. So after evaluating this expression, what happens is A is going to point to new black box, new lambda abstraction. So this is old one. So this is old. And now A is going to point to new lambda abstraction to be constructed here. Okay. So this one will be this one, the new integer array. So integer array, so therefore you have to create the function of this type, int arrow int. So given an index j is integer, let's first check if this j is equal to this integer I. So if j is equal to I, then what happens? So we wanted to update this integer array A with a new element n at index I. So the given index is I, so therefore you have to return n. Otherwise, you are trying to access not the old element, not at the index I. So in that case, you just go back to the previous integer array and then retrieve the element. So therefore, you call this old with index j. So that's how you implement this update. So notice that we use the three new constructs for mutable references somewhere. For example, here you use this reference construct, and here you use this bang dereference, and here you also use bang dereference, and finally here you use this update. So you use all these three new constructs for mutable references somewhere here. Now, this is the correct answer, but what's more interesting is actually a wrong answer. The wrong answer for this update is something like this. Update is, so this is wrong answer. Update is lambda a integer array give me an index I and give me new value. And then what I do is I directly update without taking a copy of the current value. So this part is gone. And I directly updated this A with new lambda abstraction. If j is equal to I, then you return n. Otherwise, in this correct answer, you made a copy of the old array. So this lambda abstraction has been saved in old. But now you don't have this one. So the only way to get access to the lambda abstraction is to dereference itself. So here you use bang A. And it's pretty easy to see why this is the wrong answer. If this array is accessed with index I, then things are okay because you are going to return n. But that's not the case. For example, if you provide a different index, then this then branch is never taken, and you always take this else branch. But when you take this else branch, you have to dereference the same location, the same integer array. So you go back and then evaluate again. So the wrong answer is actually bang A applied to index j. So you make a function call and you go back here, and then you find that the argument of j is still different from index I. So again, you take this else branch. So now you are in a position where you visited previously, and you make essentially you make a recursive call. You go back again to this lambda abstraction, and then take else branch again, and so on and on. So this loop never terminates. So essentially, you triggered an infinite loop by taking this else branch. So we accidentally discovered how to implement recursion or infinite loop. So remember that when we discussed the fixed point combinator for the first time, we tried to find out a lambda expression whose reduction never terminates. So we talked about this omega expression. And the presence of this omega expression was strong evidence that you can actually implement the general form of recursion. And similarly here, with the mutable references, you can implement infinite loop. And you can generalize this idea, and you can implement recursion in terms of mutable references. So suddenly, after adding mutable references to your language is so powerful, it is capable of recursion or recursive functions, and suddenly your language becomes Turing complete. So so let me summarize. So you have this simply typed lambda calculus, and you add mutable references here, and suddenly this combined language supports loop or infinite loop, or more generally, recursion. So this language is Turing complete. So what this implies is that in the presence of mutable references, you don't actually need this fixed point construct, because you can actually simulate this fixed point construct in terms of mutable references. So this is introduction to mutable references. Now let's extend the language simply typed lambda calculus with the mutable references. So there are three components to visit first: abstract syntax, and then operational semantics, and then type system. So let's extend the abstract syntax first, and then develop the operational semantics. So the types, we have base type and function type. And for simplicity, let's not talk about base types. Let's assume that we have many base types such as bool or integer and so on. And expressions, we have variable lambda abstraction, and application. And now we are going to add new forms of expression. First, we need a unit type. For example, the assignment expression will evaluate to unit value. So we have this unit value and also unit type. And we are going to add this reference type for mutable references. And the three corresponding language constructs are this reference. We have this reference A. Notice that we reuse the same keyword in different contexts in the definition of types and also in the definition of expressions. And this is now ref A, ref E. We have this dereference, bang expression E. And finally, we have this assign. So that's the new language construct for mutable references. So this is fine as far as writing your program is concerned. But once you consider how to reduce a given expression, we realize that something is still missing. So for instance, suppose that you have reference expression E. Probably you will keep reducing this expression E and generate, let's say, reference, some value V. Then, according to the design that we saw previously, this reference V is supposed to return location L. But location L is not currently included in this definition of expressions. And in fact, this location L is some sort of runtime value that is not supposed to appear in your source code. This location L will be available, will be generated only at runtime, not at compile time. So nevertheless, we have to extend the definition of expressions to include this new form of expression called location. So we add this location L. But remember that this location L is not supposed to be found in your source code because it's going to be runtime or dynamic value that is generated at runtime, never at compile time. So in the real implementation of the language, this location L will be literally a pointer or address. Inside the process. So therefore, it's not available at the compile time. So that's the thing that you want to keep in mind. This is called the location. And it is not part of your source code. It will be generated only at runtime. Now, let's talk about the reduction judgment. So we'd like to use this reduction judgment, and the previous reduction judgment has this form, expression E, reduced it to expression E prime. But now we have these location references, and we definitely need to extend this judgment. So for example, how do we reduce this bang expression E? Suppose that this bang eventually produces bang location L. So if this is well typed, probably this has ref A. So expression E has type ref A, so that the whole expression is type A. So if everything goes okay, then we would have bang location L. Then how do we reduce this one? Bang L. So the semantics is, if at this moment, if L is pointing to a memory cell that contains a value V, then we will reduce it to value V. But this reduction judgment says nothing about the mapping from this location L to memory cell. So it turns out that this one, the mapping or the collection of mappings in abstract form should be part of the reduction judgment, so that we can, for instance, reduce this bang L to value V. Without access to this mapping, there's no way to reduce this bang L expression to a concrete value V. So what that means is that the mapping from location L to value V, let's say L, arrow V, mappings of this form should be part of this reduction judgment. Otherwise, there's no way to reduce this bang L. So this observation leads to the introduction of something called a store. So the basic idea is that this mapping that says location L is currently mapped to value V should be part of this reduction judgment. So we introduce something called a store. Store is basically mapping, collection of mappings of this form. So for example, currently location L1 is mapped to value V1, location L2 is mapped to value V2, and so on. This finite collection of mappings is called store. And we use this meta variable psi. So psi is basically empty store or an existing store extended with this new mapping. Location L is mapped to value V. So you can think of this store as some abstract representation of collection of memory cells. So in real implementation, we don't have these locations. Instead, we have addresses. So 0x01, 0x02, and so on, 0x0a, and so on. And we will have some values here, v1, v2. So this is the what we will see at runtime inside your machine. But in this formulation of operation semantics, we need some abstract way of representing these memory cells, and that's what this store is for. Okay, so store psi is just a collection of mappings of this form. Now we have this store as a part of this reduction judgment. So the reduction judgment now has this form: expression E with the store psi reduced it to expression E prime with the psi prime. So this expression E prime is definitely distinct. It's not equal to expression E. But this new store psi prime may or may not be equal to psi. So for instance, if expression E involves no mutable references, then no changes are made to this store. So in that case, this psi prime would be equal to psi. There's no change to psi. On the other hand, if expression E creates new memory cell, if it allocates new heap cell, then, or for instance this one, if we update an existing heap cell, then this new psi prime will be different from this psi. So that's the thing that you want to remember about this judgment. So this judgment says expression E with store psi. This is the current state, and this one reduced it to expression E prime with store psi prime, where psi prime is potentially updated, but not necessarily. So with this interpretation in mind, now it's actually pretty easy to develop all these reduction rules. So let's see the reduction rules. So remember, the judgment is expression E psi reduced to expression E prime psi prime. So first, the reduction rules for application. So the previous reduction rule was If E1 reduced to E1 prime, then we will have E1 prime E2. And intuitively, we just carry the stores from the premise. So for instance, if you have psi here, you will start with So if you have currently stored psi, then you reduce expression E1 under psi, and if this one produces psi prime, then you end up with a psi prime. And similarly, we can extend the rule for lambda. Let's say the argument is expression E2. If the current store is psi, then it's time to reduce expression E2. So expression E2 under psi reduced to E2 prime, psi prime, then the whole expression applied to E2 prime under psi prime. Finally, the third case is also easy. Lambda x e applied to value v. Let's say the current store is psi. Then it's time to apply beta reduction. So v for x in expression e under psi. In this case, there is no change to store because its beta reduction has nothing to do with the mutable references or location. So we carry the same store over here. And what about this reference? Suppose that we have a reference expression E under psi. So first of all, you have to reduce expression E until you generate the value. So the first rule is easy. Suppose the expression E under psi reduced to expression E prime under psi prime, then the whole expression reduced to reference E prime with the psi prime. If everything goes okay, then well, you would have reference value V with a psi. Now it's time to allocate a new memory heap cell. So in this case, let's say this is psi. What you want to do is you create a new memory cell associated with location L, and then you initialize it with value V. So suppose that you have some way to generate the fresh location L. Then what you do is you return location L and you augment the store psi with the new mapping L arrow L mapped to value V. So in the course notes, instead of using fresh L notation, we use this domain. The domain of this psi does not include L. So in the course notes, we write L is not found in domain of psi. But basically what this thing says is L is a completely fresh location that has not been generated before. So that's how you evaluate the reference. And what about bang? Bang E. So the first rule is easy because you should keep evaluating expression E to generate a value. And in this particular case, this value is going to be a location. So expression E under psi reduced to expression E prime psi prime. Then you have bang E prime psi prime. And if everything goes all right, then you do have bang value V. And this value V is location. It can't be another form of value like integer or boolean. It must be a location. And you have this store psi. And suppose that this psi currently contains L arrow value V. So currently location L is mapped to value V. Then what you do is you return value V. That's all. So in that case, you never update this store. So the store is the same. And in the course notes, we use this notation L arrow V is found inside. But basically what this thing says is somewhere inside the store psi, you should find this mapping. And what about is assign expression E1, E2 under psi. So the first two rules are straightforward. So for example, expression E1 under psi reduced it to expression E1 prime, psi prime, and this one reduced it to E1 prime, sine E2, psi prime. So it's easy. And if everything goes all right, then you'd have location L assign expression E2 under psi. In that case, you keep reducing expression E2. If this one reduces it to E2 prime with a new store psi prime, then you generate L sine assign expression E2 prime and psi prime. And if everything goes okay, then eventually you will generate something like location L assign value V this time. So in this case, what we want to do is, first, we make sure that currently L is mapped to a value V prime inside this store psi. Otherwise, it's semantically wrong. You can't do anything about it. Basically, you get stuck. You get stuck if you don't have a mapping of this form inside, because you are trying to update the contents associated with location L. So therefore, there must be some memory cell for location L inside the store psi. So if this is not the case, then there's nothing you can do about this assign. So let's make sure that this is the case. And then what you do is you simply update this value V prime with the value V. And let's state the resultant towards the psi prime. And the notation that we use in the course note is psi prime is psi where this mapping has been updated to value V. But you don't really need this notation, because what we need here is, it's just that the current mapping is cancelled and new mapping is installed, and the new mapping is basically L is mapped to value V. That's all. So if we use this notation, you'd have L arrow V psi. That's all. So the syntax may not be familiar, but the key idea is very simple. The key idea behind this reduction rule, for example, is you return unit value here, because the result is not interesting computationally, so it suffices to return this unit. But anyway, the key point here is simple, the key idea. Inside psi, you do have something like L arrow, some memory cell, and in the memory cell you have the previous value V0. Now you update it with the value V. That's all. So what we did here is we introduced a new form of reduction judgment, and we developed the reduction rules like this one.